Hi everyone, I'll be presenting our paper, LineVD, Statement-Level Vulnerability Detection Using Graph Neural Networks, co-authored by Andre Khan and Huaming Chen and supervised by Professor Ali Babar. Each year, data from the National Vulnerability Database, or the NVD, show that more and more software vulnerabilities are being discovered and reported. Software vulnerabilities can lead to devastating effects, such as data breaches, which can cost companies both financially and their reputation. As a result, it's becoming more and more important for developers to be able to identify software vulnerabilities efficiently and as soon as possible in the software development lifecycle. Most of the current data-driven automated software vulnerability detection approaches are usually coarse-grained in their outputs, so for example file level or function level as seen on the left, compared to fine-grained, so statement level as seen on the right. Vulnerabilities can often be localized to a few key lines, which should be reflected in automated software vulnerability detection approaches. This is what we aim to do. As of the time of writing, there's only one other similar work, following the line of using interpretation in order to detect software vulnerabilities at the statement level. Here, we describe the main similarities and differences between our approach and an interpretation-based approach. That is, whether or not the model directly trains on statement-level labels, whether we require an additional explanation step after each inference on the trained model, and whether the model can output a list of the most confidently vulnerable lines. In developing a statement-level prediction model, two fundamental problems are how to represent statements and the relations between statements, and how can we efficiently apply learning over such representations. These are the problems we consider when developing the LineVD model, which I'll be going into detail next. First, LineVD is designed to extract the code features against the transformer-based model, which is considered as effective for source code-related tasks with the self-supervised learning objectives. For example, given a functional statement, the pre-trained transformer is able to encode the tokens into a latent vector representation. Next, in order to capture the relations between lines of code, data and control dependencies between lines of code are extracted, as vulnerabilities often include data and control flows. The graph attention network was used in LineVD in order to apply learning over the statement-level representations. These two modules are combined in the final LineVD model, which is trained end-to-end. In particular, a given function and its statements are encoded accordingly before being passed through a series of fully connected layers, with probabilities of each statement being vulnerable as outputs. One key part of our architecture is that we encode both the full function along with the statements that are encoded through the graph attention network through the classifier, and pass both through the same series of fully connected layers. To investigate the performance of our model, we answer the following 5 research questions. First, how much performance increase can LineVD achieve in comparison to the state-of-the-art interpretation-based statement-level model? Second, how do different code embedding methods affect statement-level vulnerability detection? Third, how do graph neural networks and function-level information contribute to LineVD's performance? Fourth, how does LineVD perform in a cross-project classification scenario? And finally, which statement types are best distinguished by LineVD for real-world data? For our evaluation setup, we used the Big Vol dataset introduced in MSR 2020, containing approximately 10,000 vulnerable samples and 177,000 non-vulnerable samples from 300 plus C++ and C projects. We use a train-validate test ratio of 80-10-10, and we follow the standard code pre-processing procedures as in other works, such as ignoring whitespace and comments. Specifically, we also exclude invalid samples from the original dataset, as we found some improperly truncated functions in the Big Vol dataset. We train the model on statement-level labels using cross-entropy loss function. These labels are defined using heuristics defined in the existing literature. First, removed lines in a vulnerability fixing commit serve as an indicator for a vulnerable line, and second, all lines that are control or data dependent on the added lines are also treated as vulnerable. Finally, we evaluate our results using F1 recall precision ROC AOC and precision recall AUC. For research question 1, we obtained significant improvement in both ranked and binary classification metrics. And another key part of our architecture is that the inference time is significantly faster for a single example. While binary classification is our main purpose, we also report rank metrics to evaluate the performance of our most confident predictions of the model and to compare with the previous methods. Regarding the code embedding approach, we find that for the task of statement-level vulnerability detection, CodeBER outperforms other popular embedding models used in natural language processing. The third research question focuses on the graph embedding component of LineVD. We test against graph convolution networks, the use of different program graph representations, and the inclusion of the function-level representation in the end-to-end framework. Based on the F1 score, we find that the best combination is using a graph attention network with a program dependence graph, that is, both the data and control dependencies, as mentioned previously, and inclusion of the function-level representation. For research question 4, we evaluate the performance of LineVD in the cross-project scenario. Using a cross-project scenario can better represent how the model performs on a completely unseen project, rather than just the unseen examples. We can see that performance is generally consistent throughout the different projects, which is good, albeit being a bit lower than the standard scenario. Finally, we investigate how LineVD performs on different statement types. We find that LineVD most often classifies function declarations, calls, and while statements, but struggles the most with continue, break, and goto statements. The key takeaways of our paper is our improvement on the state-of-the-art for statement-level software vulnerability detection using the graph embedding components, along with jointly learning from statement-level and function-level representations. The source code for our experiments and models can be found publicly at GitHub. Thank you for listening.